In the next two sections, we will discuss what makes mathematical psychology's use of mathematics different from other branches of psychology. I will be looking at this question more generally, and I will offer 4 provisional answers. I'll then hand it off to Mara, who will look at this question focusing more specifically on the relationship between MathPsych and cognitive science. So what makes mathematical psychology's use of mathematics different from other branches of psychology? As a first answer, nothing. MathPsych simply wanted psychology to embrace quantitative models. As a historical sociological fact, psychology has perennially resisted quantitative methods and models. The origins of MathPsych as a field was in part simply a movement advocating the use of quantitative methods and models. It is not part of MathPsych's essence that it advocates a particular type of mathematics. Nevertheless, the claim that the mind is appropriately studied with quantitative concepts is a bold and interesting claim, as Osman discussed in the previous section. In 1995, Duncan Luce wrote that, quote, "Mathematics becomes relevant to science whenever we uncover structure in what we are studying. The existence of psychological structure cannot be in doubt, but what that structure is another matter." End quote. In our interviews, we have heard that, quote, "All sciences move in the direction of becoming quantitative as time passes. We use quantitative modeling to be precise and to be able to communicate properly what we're doing." So mathematical psychologists seem to advocate generally for a quantitative psychological science, more so than for any particular kind of mathematics. That said, there are some trends. There are many different dimensions along which the use of math and psychology can vary, and practitioners of mathematical psychology have expressed views to us that would locate mathematical psychology in specific areas of these spaces. So, as a second answer to our question, MathPsych's use of mathematics is distinctive in that, in practice, it is more likely to adopt tools for modeling from a wider range of areas in mathematics. Partly, this is a result of MathPsych valuing advanced training in mathematics beyond basic statistics. Greater knowledge of mathematics simply means more mathematics to draw from. In particular, more geometric maths seem to appear more frequently, such as topology, group theory, and differential geometry. For example, considerations of geometry, group theory, and symmetry lay at the heart of Shepard's work on psychological spaces. These types of models may still incorporate probabilistic elements, but they nevertheless include mathematics that make these models distinct from more standard statistical models. Additionally, when it comes not to the math in models, but to the formal techniques used to evaluate models, we have heard from our interviews ways in which mathematical psychology stands out. In particular, we have heard how mathematical psychology brings together statistical inference and experimental design in a more principled way. Instead of experimental design and statistical analysis occurring as separate and consecutive stages of investigation, as is often the case in psychology, mathematical psychologists to a greater degree first establish which statistical tests will allow them to answer the question they are interested in, and then design their experiments with such a statistical test in mind. In general, our interviewees have described mathematical psychology as having a tighter relationship between models and experiment than in other areas of psychology, although people will disagree on what this means exactly. One sense in which this is true, however, is that the norms for evaluating models with a clearly specified mathematical form relative to data are more established than in the case of, quote, numerical simulation models. That is, quantitative computational models that may not have an apparent or specifiable mathematical form. MathPsych has traditionally valued having models with a clearly specified mathematical form so that the model's properties, transformations, and evaluations can be better understood. This then leads us to our third answer, theoretical math, analytic solutions, and hand-fitted models. MathPsych is distinctive in part in that it has always included branches that focus on pure mathematical results, such as those attained in measurement theory. And then MathPsych modelers of empirical data have expressed preferences for analytic models and models whose features are not derived from automated procedures, but are instead chosen by scientists. Many figures in MathPsych have expressed concern over the ease with which computers can help produce predictively accurate models. In 1975, Bill Estes wrote of the computer revolution, quote, "The fitting of the model to data is accomplished via computer programs with 4, 8, 12 virtually unlimited numbers of parameters being evaluated by computer search of the parameter space, almost completely bypassing both the opportunities for ingenuity and the quantities of blood, sweat, and tears that used to go into this enterprise. It has become almost literally the case that the fitting of a model to a set of data is primarily a test of the technical competence of the investigator and has little to do with the adequacy of the model for interpreting empirical phenomena." End quote. So while MathPsych has embraced the use of computers to automate the fitting of models and the like, there is still a desire for models to be generated and evaluated in principled ways that go beyond the desire for mere predictive accuracy. Again, what this looks like is not agreed upon, but I will attempt to say a bit more about what this might mean in our fourth and last answer. So our last answer, aspirations for general, abstract, and well-supported cumulative theory. Mathematical psychologists frequently express a strong desire of attaining well-evidenced, mathematically expressible psychological theory that generalizes beyond a particular experimental context. This is arguably what makes MathPsych different from, say, psychometrics. This means models that go beyond descriptive summaries of the data, go beyond merely establishing effects, and capture underlying causal processes. Such a goal requires moving beyond goodness of fit for the evaluation of models. I'll now say briefly a bit about two ideas that mathematical psychologists have discussed that can serve as indicators that some work in mathematical psychology is achieving this goal. So the first is the idea of a model providing insight into how to lump and split data from diverse experimental contexts by capturing causal processes. So lumping data occurs when seemingly disparate mental phenomena can be shown to be subsumed under a single general model. Again, Shepard's laws provide a good example. And then splitting data occurs when seemingly undifferentiated behavioral data can be shown to be quite naturally carved up and shown to be generated by distinct submodels of cognitive processing. Attah's 1975 gives the example in classical physics of the wave and particle models of light capturing different aspects of complicated optical phenomena. And then in the case of psychology, Attah gives the example of Stevens' 1957 categorization of prothetic versus metathetic sensory dimensions in relation to scales of measurement. I invite you to think of any examples that you can. So lumping and splitting are both valuable and illustrate the goal of moving beyond mere predictive accuracy toward well-evidenced general theory. The second idea concerns the nature of cumulative theory. Duncan Luce wrote in 1995 that it is moderately rare to find a psychologist who, when confronted by a new set of data, invokes already known mechanisms with parameters estimated from different situations. When each model is unique to a particular experimental situation, all of the model's free parameters must be estimated from the data being explained. Frequently, the resulting numbers of parameters outrun the degrees of freedom in the data. This reflects a failure of the science to be cumulative, an unfortunate feature of psychology and social science that is widely criticized by natural scientists. I view it as one of the greatest weaknesses of modeling and other theory in our science, end quote. In many cases, a psychological theory that adequately predicts some body of data does not generalize to new data, and so it must be modified in order to adequately predict the new data. This is a weak form of cumulative theory because it is more impressive when models of experimental findings are already constrained by previous experimental findings. Right? Here, the goal is to approach a new experimental context with a well-supported theory in hand, such that the new data, together with the well-supported theory, entail new psychological theoretical posits. In this sense, when this happens, new psychological facts are established through the process of theory-mediated measurement. Townsend, for example, writes that signal detection theory stands as the prototypical theory-driven methodology, since it can be employed to discern decision and learning bias from true sensory or sensitivity, e.g. signal-to-noise ratio effects, in such diverse fields as hypnotic phenomena to trial witness memory to laboratory psychophysics or learning and cognition experiments, end quote. So this process of evidence, again, illustrates a desire to go beyond goodness of fit. So while not unique to mathematical psychology, these aspirations that I've just been discussing are voiced strongly by many mathematical psychologists. And there's a sense of optimism at the possibility of attaining these goals and a belief that we shouldn't lower our standards. Because just as many psychologists eschew the use of math in psychology, many psychologists feel that we are not entitled to these sorts of lofty scientific aspirations. But mathematical psychologists have expressed that we must attain this goal if we wish for psychology to ever become a, quote, mature science. So I now hand it off to Mara, who will discuss this question we have been looking at as it pertains more specifically to the relationship between mathematical psychology and cognitive science.